and welcome to my channel where I learn how to be a self-regulated learner. So what we will do today is our first mind map brain dump of my thermodynamics course. So this is a theory technique. I am learning it from I Can Study. I haven't learned it the way they have taught it yet, but it is a part of interleaving. So if you want to know more about interleaving, just tell me. I'll work on it. Right now, the focus is on mind maps. The point of interleaving is just to look at the same information in a different perspective while retrieving it. A mind map brain dump emphasizes on the ability to be able to draw connections in the theory that you have learned, and even maybe prioritize the information in different contexts. The thermodynamics concepts that we will be exploring range from temperature. We have temperature. We will be looking at heat and thermal energy. We will be looking at heat capacity. By the way, this is part of the mind map brain dump. You want to put the first keywords in and then draw the map from there. So this is all coming from memory. I'm trying to retrieve this information. A lot of this I haven't seen in over a month. The recent information is more advanced, and I haven't practiced much on it. So we'll see how that goes. So I have heat capacity. Let's see. Kinetic energy. And we're going to put potential. Can come hand in hand, kinetic and potential energy. We have the ideal gas model. Ideal gas model. By the way, I really want people who watch these videos to, tell me what I did wrong, what I did right, because this is really, I've been trying to do these, but this is my first time actually submitting something for feedback. This is part of the challenge of doing 1,095 days to become a self-regulated learner, maybe even a learning coach with I Can Study, which is my dream. So yeah, let's get into it. Ideal gas model. We have entropy, enthalpy. By the way, I'm really bad with spelling, so I might have written that wrong. Not sure. So what do we have? We have omega, which is basically I'm going to put omega nu, which is basically we have like microstates. Microsystems, yeah. Microsystems, I think. We'll check everything at the end. The whole point is to actually retrieve the information. What else have you looked at? Well, we have the ideal gas law, but this time I'm not gonna write it. So it's PV equals nRT. However, it's also equivalent to PV big N kBT. Okay. What else do we have? What else do we have? We have U, well, we have something very important. What are process variables versus state variables? Now, I believe we have an extensive list of keywords. We can get started right away. So, what's the idea, the most important idea in here? I think we should start by looking at entropy as being the fundamental idea. It's not the one we started with, but I feel like, and we're going to test that, entropy and enthalpy are at the basis of all my understanding of everything around it. So let's start with that. I'm going to call entropy here. Let's see. Let's go closer. Good. Entropy. So gonna go put it in the center there. Okay. And now, what is entropy? Well, entropy is the measure of disorder. Okay, so we have, it's a measure of disorder. I'm also going to prioritize it for the moment this way. Okay, so it is a statistical process. Entropy is well, I know what entropy is. The point of the mind map is to relate the keywords to each other and concepts to each other. It's harder than I think. It's harder than you think. It's harder than I thought. It's really hard. Okay, so first of all, let's look at entropy is a state variable. So this tells us something important. Entropy is actually a state. Entropy is a state. I'm gonna make it smaller. And yes, I do ramble a lot in these videos, so if you get bored, I'm sorry. I'm really sorry. Okay, so entropy. Let's just try this. Is a state variable. State v. Oops. Now, what else is a state variable? Also, it is the measure of chaos. I'm going to put measures chaos. It's also based on probabilities. So it's a so it has a statistical properties, which we will explore. And I'm going to combine a bit of Feynman here. So I'm just going to say it in the video, but entropy is basically the flow of usable. Well, so here's a mechanics engineering definition of it. It is, so the increase in entropy is basically the decrease within a system. It's important to state that when we look at entropy, we have to look at it as a state variable of a system. So this is important before I move on to anything. And it measures the chaos of the system. And it also looks at the statistical properties of the system. Now, entropy is tightly linked to energy. And here's why I'm telling you this. So here we have energy. And I'm writing it in another color because energy is actually, I think, even more central to thermodynamics than we think, because we have, so here we have thermal energy. And by the way, I know it's very chaotic right now, uh, no pun intended. Uh, but the first mind map is not supposed to be the good one. It's supposed to be the one that gives you insight. The next mind map is where you order things out and you add information. So you redo it. And these things take time, but they do help with creating these very deep connections that can last months. Well, in my case, it's not the same for everyone. I know that in my case, when I use these mind maps, I, I, I can remember things for a very long time. So we have thermal energy, we have kinetic energy. And I think I'm going to put potential energy here because uh, kinetic energy is closer related to thermal. So potential energy. And we have kinetic. And this will also be a bit of a basis to the documentation that will be putting on Obsidian, uh, which you'll have a link to down in the description, where I actually try to document my work in physics, math, learning, and teaching, and make no promises of anything being completed at a time where you open the link, but usually you will find a lot of information that you can navigate through even with an interactive graph explaining things. So what is thermal energy? Thermal energy is just the kinetic and the average. Okay, so thermal energy. Hmm. It's a hard thing to describe. It's the I would say it's the kinetic energy of an entire system of particles. So the thermal energy of a system, thermal energy, is actually kinetic. And here what I'm gonna do, I'm gonna say kinetic. So, so here we're gonna add a new word, which is, just gonna call it particles. So I don't know why, but I'm gonna call it particles, which is, it's not that central, but it's important. So call it particles. And basically what I'm saying here is that kinetic energy of particles give thermal energy. So basically thermal energy is the kinetic energy of particles. That's it. That's it. So, and when you have a soup, so we can even draw here a soup. So this is like having a, I'm gonna draw the soup here. It's like having a soup of hot little particles that are just wiggling around. And this gives you thermal energy. Now, let's go back to entropy. So when entropy increases, basically, the overall energy stays the same. However, there is a transfer of energy type. So here we're going to look at the energy types. We have, I'm going to call it, so thermal energy is Nu. So usually it comes into, which means not useful. It's very useful, but it's just in the definition of it, you would call it not useful. So, which means basically that you cannot do work. So not useful means, well, in the potential, let's say, potential and kinetic energies, they both, so work in creates potential and work out creates energy, kinetic energy. We call this work. Work. So work is important. And the useful and not useful part of this diagram, of this mind map. So basically, if work can be done, then it's useful. So we can call it U. Work means useful energy. So we're going, so when we do work, we go from U, we can do this. Work is basically going from U all the way to not U, usually, in a thermodynamic process. Because you can go from U to U. For example, running up the stairs. If you are a perfect system, no energy leaks, you go from kinetic to potential. Then you drop down. Gravity is doing the work, so still useful. But usually this in a thermodynamic process. In a energy in a thermal energy transfer. Well, yeah. This is in the transfer of thermal energy. Perfect. Now, let's see. What else do we have here? So we looked at work. Now let's look at statistical properties of the system based on entropy. How does entropy relate to energy? That's another good question. What are the equations for these things? This is something that I think I'm going to do a different mind map. So this is for the concepts. And then we're going to explore the equations and how they relate to each other. Probably going to do it on an Obsidian note because it's going to be very good for research. So I'll be able to actually, yeah, to actually use that documentation. So let's look at temperature. Temperature. So what is temperature? Temperature. So let's see, I'm going to put temperature here. So we have particles. So let's look at this like this. I'm going to put average. Gives me temperature. Now, let's see. Going thermal to work. I wish this was a three-dimensional thing, but I can't go behind it. So I'm just gonna say that basically, here I'm going to say thermal energy plus work, and I am using it second time, it's fine. Thermal energy plus work, I'm going to put like a small dot to say that I used it once again somewhere. That gives me heat. So the work of thermal energy is heat, I believe. I hope this is correct. I really hope this is correct. So this is a great opportunity to mention that I just found a gap. So how are we're gonna do this? For all gaps, I'm gonna point them in green. Okay. So now this is a gap. What does a gap mean? A gap means that I am unsure of my answer. And it's very important to be sure of your answer. Confidence is a better indicator of mastery over the information that you have. So this means that I need to look up the relationship between heat and work, and that's fundamental to all the exercises that I will be doing. I think this was also a hard thing to actually. So I don't know if this relationship was correct. So I wasn't confident about that either. I think that here relating entropy to statistics. So I'm gonna just. I know it is, but I don't know if it's statistical properties specifically, or process, or a statistical entity. I know that entropy, since it looks at the chaos within a system, it's also the reason for causality. I'm gonna mention that. But I don't know exactly the relation. So basically, if things could rewind, so things cannot rewind. This is the rule in entropy. If things cannot rewind, then we have causality, which means that something can cause something else to happen, and you can't undo that. There is a print in reality, and that is actually time. Causality is time, is the flow of time. So the forward flow of time. Forward time. Okay. Now, something I just noticed while writing this is that I didn't mention that we have the thermodynamics principles, and these should be basically my reflex, which is also an indicator that I have weak prioritization, but we have the zeroth principle of thermodynamics. We have the first principle, and I don't remember these, not all of them, so this is what we're going to try to do. We have the second law. Oh, these are not principles, these are laws. Yes, these are laws. You see, this is how weak my encoding, well, my prioritization of the information was. So these are, I was too invested in the details of understanding how they work. I didn't really look at how the different laws affected the different concepts and in what way. So let's look at, I think the best way to do this mind map next time is to actually see in each law, which concept plays a stronger or more important role, and then we're going to look at how the laws interact with each other and what combinations we get from them. What concepts emerge from which laws? So we might have like pure concepts, which are purely based, for example, from the zeroth law, or we might have concepts that are derived from all three, which would be more complex, constructed. So my hypothesis would be like heat engines would be based on probably almost all three laws, all four laws, because we have a third one. I think we have a third one. I'm not even sure. And we have the third law. So yeah, let's look into that. So before that, let's see. We talked about temperature, right? Talked about temperature. Tried to talk about heat and thermal energy. We did not talk about heat capacity. Kinetic potential energy was mentioned. Ideal gas model, haven't talked about that. Entropy, not enthalpy. The omega and u, which is the number of permutations of energy states within a microsystem. We should also talk here about the multi multiplier. Multiplier. Um, we did not look at the equations yet, process variables and state variables. I didn't mention what they are. So what is a state variable? This is important. So state variables. Let's look into these. So state variables, actually this is perfect. I'm gonna take the concept of time as a subcategory. And I'm gonna say that state variables do not change. Well, it's not in time. They do change in time. I think they don't change. They are not path dependent. So yeah, state variables are, so let's put it here. Are not, so I'm going to put path dependent. What does it mean to be path dependent? Well, path dependent means that, I'm going to explain it here. If you were to, let's say you were to heat up a stove full of water. Okay, so you're heating it up. Okay, this is my flames. This is the best flame I've ever done. So you're heating it up, and the water boils. Now, the path you take to transfer. So here we have a heat transfer. Heat, and this is important because the metal pan's heat capacity plays a role in the path. Okay, so this is important. So let's look at this. This is a good introduction to heat capacity. So say you heat up the pan and you heat it up real quick. So you take 1 second and you move from 20 degrees Celsius to 300 degrees Celsius. Boom, real fast. Okay, what happens here is the energy transferred will transfer differently. So the heat will be different. So let's say this is case 1. Okay, so heat 1 is different than heat 2. Now what's heat 2? Heat 2 would be like, let's say it takes 1 hour to move from 20 degrees. Of course, we're looking at Celsius here, but Technically, it would be even better to have kelvins. This would be a good introduction within temperature to say that kelvins are the standard, let's say, let's say 400 Kelvin, 500, and say 500 Kelvin here. And we're gonna look at, say we start at 200, well, 290 degrees, 90 Kelvin, okay? And then we do the same thing, but it takes us an hour. So one was in a second, split second. The other one is an hour, okay? The heat transfer is different because of the barriers, because of the interactions between the water molecules. It is different. How different is it? That's a very good question. Like, what's the main difference? What happens? Well, this is what we call processes. So we have, these are time-dependent processes. Time-dependent. So the path is a different path in time. So the path dependency is a different path in time. And they have many effects on energy transfer through the material, etc. Now, heat capacity is the amount of heat that a material can transfer or endure through time. So, and I'm not sure exactly what's the definition. It has to do with the amount of energy. So it's the amount of energy to evaporate liquid water. That would be, well, yeah, that would be, so it's an amount of energy. This is a good start to finding back there. So it's an amount of energy, and I think it's in calories. Yeah, so it's in calories, and basically one calorie is the amount of energy needed to evaporate liquid water. How much liquid water? I think it was 1 centimeter cube, I believe, is, yeah, yeah. Okay, well, we know this is a volume, and volume depends on pressure, so I'm gonna look at mass, which is not dependent on anything else. I think it's 1 gram of water, 1 gram of liquid water. We evaporate that, we get 1 calorie. So back here, we know that heat is a process variable. Process V, and it's also dependent. So this means that it is path dependent. So here, I'm just going to do that. This is a bad practice, by the way. You should not be doing this. You should have your informations close to each other in the mind map, but I don't know how to do that yet. So it is path dependent. It is path dependent, process variable. And one of the paths that it can depend on, we have time, which, yeah, basically mentioning a second time here. We have material, So it can go through different materials, or maybe even a better word would be medium. Medium. Yeah, and we're going to look at processes in general. So we have processes. Processes. Now, within systems, I did not mention that, but we have three types of systems. Still haven't talked about laws because I'm not sure about them. I'm trying to, get a better grasp of things for now. So I think we've talked about heat capacity here. The ideal gas model, not yet. Microsystems, a bit. Did mention that. Did we? Hey, where did we mention microsystems? We did not mention microsystems. Oh, my bad. We did not mention microsystems. Nope. Okay. So what was I saying? ADHD hit again. ADHD hit again. What was I saying? Oh, this is annoying me. Path dependent, time. Well, we did talk about this. I can't remember it. That's okay. It's fine. We'll come back to that later. So, particles, averages. Now, yes, I just remembered. Systems. So, we have three types of systems. Let's look at these. And this means that I also have, so these are the more old information. So we have closed systems. We have isolated systems. And we have open systems. Now, the main idea here is you want to understand that closed means there is no change in heat and there is no change in plus no, well, I'm not gonna, these symbols are bad. I'm gonna say delta Q, just gonna say delta Q equals 0 equals delta N, which means that the number of particles does not change, so nothing goes in, nothing goes out, and the heat does not change, so nothing can heat it up from external, so external heat. So the change, so no external heat comes into the system, so there is no, so this is no change in internal heat. Internal number of particles. Oh, sorry, that's for isolated. My bad. So I'm just gonna change the words, but yeah, this is for isolated. Closed means that you have a change. So isolated. My bad. Closed. So what do we have for closed? Closed, we have change in heat different than 0, but 0 is change in internal number of particles. Open is both change. So delta Q different from 0, which is different from delta N internal, obviously. So yeah, that's what we have. So these are the systems. So this is where you would put them. So we have three types of cases. Closed systems, isolated systems. And I'm going to try to make boxes for each one of these. And we have open systems. And each one will have their state variables Okay, so these right here, state variables will be different, will interact, will change differently. And that change of state variables does happen because of the process variables. So let's say the change in heat, so how heat is transferred, will change the average temperature within a system, so the average thermal energy, which is the temperature within a system, depending on how the thermal energy is transferred or dissipated, for a matter of fact. So yes, we've been looking at how energy goes in, but we also have how energy goes out. Okay, so now I just remembered a lesson that I was doing, which was the Carnot cycles or the heat engine. But heat engine. And basically a heat engine can also be a reverse heat engine. So we have heat engines and refrigerators. And these I've studied extensively because I had the homework. Probably we'll cover that eventually, the homework. Look into it more. But yeah, this is looking messy and ugly, but it has helping me retrieve more information, remember things, get my mind back rolling, making some connections here and there. And it's giving me ideas to study better for the next time. And honestly, I've been procrastinating doing this for a long time. But yeah, this is a good start. So current cycles, obviously we consider current cycles to be in open systems usually, I think. Well, depends a lot. No, current cycles don't have anything to do with that. So let's say it has a lot to do with a lot of things. I don't know where to put it because I want to put it everywhere. So here's what we're gonna do. We're gonna put it, um, yeah, I'm gonna put it here. So here, because, okay, so var process variables go through different processes. So let's say we have heat within, okay, so I think current cycle has its own thing. So I'm gonna say current cycles use path dependencies. Very hard. I'm just gonna put it on its own. So Carnot, basically this is Carnot en français. Carnot cycles. And basically what we're saying here is that we have, and honestly, pretty shaky why we're looking at pressure, probably because of we're looking at this in an ideal gas, obviously. So we have pressure and volume, and this is where the model comes in. So here it's current cycles, I'm going to say plus an ideal gas model. Because there are current cycles outside of that, but I haven't learned how they work. But yeah, ideal gas. So here we have the first position. Then we have a drop. We have a different drop here. I think the curves are different. I think the curves were this way, then that way, this way, that way. And basically here you have a adiabatic, in this case. Yeah, adiabatic. So this way would be heat engine. That way that way it would be refrigerator. So adiabatic, here it's isothermal, here it's adiabatic, here it's isothermal. And this is a path, a process. And basically this means, adiabatic means that the heat, the change in, the heat change is equal to 0. So here, from going from point 1 to point 2, we have no change in heat. Going from point 2 to point 3, isothermal means, guessed it, no change in temperature. Yeah, temperature. No change in temperature, which means that delta T is equal to 0. And yeah, that's it. So then you go back up. And yeah, basically the work done, what I understood was the curve, it's the surface area of that function, which means it's an integral somewhere. And this is very useful. This is so useful in so many ways. Basically, if you want to heat up something, understand how they work. Now, let's look at the laws. After that, we're going to conclude how I would study things next time, because I think it's already a lot of rambling. So let's look at the laws real quick. So I believe law 0 was if A, so it's temperature transfer. So if you have 3 bodies, A, B, and C, okay, and we have infinite time, and T1, T0, T2, basically, and they are close to each other. So we have contact. This is contact. There is contact. What this means is, if B stays very long close to C, and A stays for a very long time close to B, then T0 equals T2 equals T1, which means that the temperature for A is equal to the temperature for C, because there's a equilibrium of kinetic energy within the system. And yes, within the ideal gas model, we can simplify a lot of things and find kinetic energy, then relate it to thermal, etc., etc. Oh, related to internal energy in general, and so on and so forth. The first law of thermodynamics, that I don't remember. The second law I do. I think this is the 0th law. The first law is probably about, I think this is the first law, if I'm not mistaken, is that the change, so this is 0, 0th. Okay, very important. So now let's look at the first. The first, if I remember correctly, was that the change, so the change in internal energy is equal to the sum of the change in heat plus the change in work. This is our first law. It talks about, so here we talk about average thermal energy through time, which is temperature through time. Here we are looking at the overall internal energy and how it varies depending on the heat change and the work change. Okay. Now let's look at the second law of thermodynamics, which I believe it's about entropy. So we have change in entropy is bigger or equal to the change in heat through time, and this is in a, I believe, quasi-static. Quasi-static process means you have infinite time between each step slash um, yeah, between each step. So going from a very small e that tends to 0, almost equals to 0. Let's call it little e that is almost equal to 0. And so for every, so when q plus, so t plus e takes an infinite amount of time. That's basically it. Third law, I think it's about the Boltzmann constant. I don't know exactly what it is. So here I'm gonna say, I already stated, the laws, they're shaky. What else is shaky? How to integrate these things together. I just don't get it really. I don't have a really deep grasp on it. I have some good relationship stuff. Now, I would love to actually document things uh, through the lens of three keywords that I found while doing this. I haven't even talked about microsystems because they're fairly new to me. So let's look at these in depth. So I think next time, so for the next time, you can write it in red. Next time. Okay. We are going to go and do something. We are going to look at we have concepts. Okay, we have the overall concept. This is like the building. Okay, this is like the building. Then within that building, we have the laws, concepts, and then we have the laws. So how do the laws apply to the concepts, to the building? How do they affect the dynamic of the building? So here we have a dynamic. And then we're going to look at the type of building or the environment within the concept. So here we have so the big frame, the environment. Okay, and that would be, for the environment, that would be the system type. And obviously the system type will be a defining factor of the concept. So the building will be purely dependent on its environment, so to speak. It's basically saying what type of building is this? What is it made of? How many openings does it have? And I believe we can look at then how, yeah, so let's start with this. I think let's start with this. Eventually you would link concepts. So how would they work in the same environment? And the point of these is to find gaps. It's to find, where am I shaky? Where am I not confident in explaining these things? And this will help me identify gaps to, solve stronger problems with more confidence and actually have mastered the material that I've been learning. So link concepts together plus prioritize. And I am probably going to look at, I wanted to look at something important. What was it? What was it, Martin? Ah, yes, the infinities. So I want to look at edge cases. So I want to look at the effects of each variable reaching edge cases. The most common one would be for temperature to almost reach 0 Kelvin. So we'll look at these. And yeah, thank you for watching. And next time we'll look at how I document the equations on Obsidian. Really happy to have got you to go through this with me. Please do help me out with this. Give me your pointers. This will help tremendously.